Hi all, so today we're going to be starting off going over the quiz 3, which covers chapter 14 and 15, so that includes electrophilic aromatic substitution, identifying aromatic compounds, and how aromaticity affects acidity are the big things. So we start with an electrophilic aromatic substitution. Step 1, this is also kind of a pre-step. Sometimes it's not counted in the actual reaction mechanism on like the ACS exam or your med school exams. Let me see if I can get that shadow. Okay, so this is generating the electrophile. Step 2 is the benzene attacks. Spelled benzene wrong. Benzene attacks. And step 3 is aromaticity is restored. So we generate the electrophile. In this case, it'll be Cl+. I know that based on it being Cl2. So we have Cl with FeCl3. And so this chlorine is going to attack this iron, and as it attacks, this bond actually is going to break. So that leaves this chlorine now bonded over here to the iron. So these two electrons join the chlorine to make 2, 4, 6, and then these two electrons created a bond between the iron. And this species is actually negative. And then this chlorine lost its electron, so that's Cl+. So that's how we get our initial first step. The next thing is benzene will attack that chlorine plus. So it needs to be something really pretty positive for the benzene to want to attack it, and chlorine does not like to be positive. So it'll attack that Cl+, and from here it acts almost exactly like an addition reaction. And I think this was a bonus point on this quiz, but in general, it is good for you to know that positive charge is actually spread. Like there's a resonance structure where the positive charge is here, and I guess I shouldn't have drawn this bracket, and another resonance structure where the positive charge is up top. Right there on that one. So you can either draw those out, or you can just draw that the positive charge is spread around the ring like this. Either one of those is okay. So that step is benzene attacks. And then the final step is, oh no, not benzene yet. The chlorine, the carbon containing the chlorine, don't forget that has a hydrogen there still. There's hydrogens all the way around. So the base that you generated in this first step will come and attack that hydrogen, and the electrons from that hydrogen, just like a regular elimination reaction, will abstract this proton. The electrons will fill in, and your aromaticity is restored. And usually it comes from this chlorine right here will be what attacks. And you end up with FeCl3 again, and then like an HBr in the solution. And this is chlorinated. So those are the three main steps: the generate the electrophile, the benzene attacks, and then aromaticity is restored. That's how I remember it. And you do need to show the curved arrows to get full credit on questions like this, both on quizzes and on exams. And then here on the back, only one of the following compounds is aromatic. Circle the aromatic compound. Okay, so I look for three things when I'm checking for aromaticity. I look for p orbitals in an unbroken ring. Sometimes Dr. Corrales refers to this as the p orbitals in conjugation with each other, but I usually think of conjugation more about the alternating double bonds. So for me, it's easier to just literally look for p orbitals in an unbroken ring. And then the next thing I look for is if it has 4n plus 2 pi electrons. And then the last thing I look for is if it's planar. And usually I remember when I was a student, I would get really caught up on this, if it's planar or not. Hang on, I'm going to adjust my camera a little. I used to really get caught up on that, like, oh no, how will I know if it's planar? It usually, if it meets these two, it's planar unless it's like an exception that you learned, and the biggest exception that you learned is 10-aniline. So I check for these three things. And what I mean when I say p orbitals in an unbroken ring is it, if it's sp2 hybridized, there's a p orbital in the ring. So if you'll go all the way back to our, there's one s orbital and three p orbitals, right? So if you have these three sp2 hybridized, there's an open p orbital that can be used. Usually it's used in double bonding, but it can also be used in achieving aromaticity. So like if there's a carbocation, it'll have an empty p orbital because carbocations are sp2 hybridized, or if it's a carbanion. And if you can't remember how to find hybridization, I have a few videos I can link to down below. Okay, so I'm going to start over here on the left. If it's a carbocation, that's sp2 hybridized, so there is a p orbital there. If it's got a double bond on it and there's a hydrogen, so it's bonded to spp2, so that does have a p orbital, spp2. So all of those have a p orbital in them. So that is an unbroken ring of p orbitals. Now, how many electrons do we have in here? They come from the double bond or carbanion, so there's 2 in p orbitals. So if we have 4 times 0 plus 2, that equals 2. So 4n plus 2 pi electrons, because there's 2 pi electrons, and then it should be planar because it's not 10-aniline. So this ring should be aromatic. But I always will check the other one just to make sure, just because, you know, I'm a nervous kind of person, so I want to be absolutely sure. So we know carbocations are sp2 hybridized, and then for it to be a double bond, it's sp2 hybridized. So this does also have an unbroken ring of p orbitals. Let's look at how many pi electrons. It has 1 from each of this double bond. 1, 2, 3, 4 pi electrons. So 4 times 1 is 4. So that's actually 4 in pi electrons, not 4 n plus 2. So it's not going to be aromatic. It's probably also not going to be planar. So if you have 4 in pi electrons, that's anti-aromatic. So this is probably going to be a pretty big one that comes up on your exam, is telling what's aromatic and what's anti-aromatic. That's like a big theme throughout these chapters. So I do want to encourage you, if you struggle to get this question right, to make sure to revisit it and that you have a good understanding of how to tell what's aromatic and what's not. Okay, and then draw the following: molecule 2 bromo 5 nitrophenol. Okay, so let's see. I'm going to start with phenol. That's one of the compounds you memorize, so hopefully you have phenol in your mind. And then I'm going to number the ring: 1, 2, 3, 4, 5, 6. 1, 2 bromo, 3, 4, 5 nitro. And that should be 2 bromo, 5 nitrophenol. All right. The next question is, only 2 of the 2 compounds given, which would be more acidic and why? So more acidic is willing to give up a proton. And if you didn't know that this was in the aromaticity chapter, I think this would be a much harder question to answer, because it's like, well, all these are sp3 hybridized and these are sp2 hybridized. sp3 hybrids are 50, sp2 are 45. I don't really know. But actually, if there's a possibility for a molecule to become aromatic, then it's going to be more willing to give up a hydrogen, because that stabilizes it. So in this case, there's not really a possibility for this to become aromatic, because there's a p orbital here and here, but all these are sp3 hybridized. So you'd have to like generate 1, 2, 3 p orbitals. So that would be really difficult. So there's no way this could become aromatic. It's like not even close. But over here, there was already 4 p orbitals. So if we could find a way to get this last one to become a p orbital, then that would be really helpful. But so if you lose a proton and you become a carbocation or a carbanion, you know, that would be a way to get a p orbital. But you have to think about what actually happens when you lose a proton, when something gives up a proton. So your base comes and it's going to take that proton, and the electrons are left behind. So it's not like you have the option to pick between a carbocation or carbanion. It's going to leave the electrons behind. So what you'll end up with is this structure. It's negatively charged here. There's still one hydrogen on there. And then it has the possibility to be aromatic or anti-aromatic, depending on if it meets all the criteria, right? So does it have p orbitals in an unbroken ring? Well, the interesting thing about lone pairs is lone pairs can go into the sp3 hybrid orbital, or they can go into a p orbital depending on which, well, two things. Is there a p orbital available? If it's not taken up by a double bond, then there is a p orbital available. Or will it help the ring? Like, is it more stable if it goes into that case? So we know there's a p orbital here, 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 and here, because all those are sp2 hybridized. So we just have to ask ourselves, will that lone pair go into the p orbital or not? Well, there's not a double bond taking it up. There's an empty p orbital, so it could go into the p orbital, and that would create our ring of p orbital requirement for aromaticity. So it gives us that. But will the lone pair actually go into the p orbital? Let's ask ourselves that. So there's an empty one, so it could. And then the next question is, does it help with the number of electrons? Well, before we had 1, 2, 3, 4 electrons, which is not desirable for aromaticity. So if these 2 electrons went into this p orbital right here, we'd have 6. And 6 is 4 times 1 plus 2 is 6 pi electrons. So actually, it will go into the p orbital, and that helps us meet the 4n plus 2 pi electrons. And then if it's got those 2, it's usually also planar. It's not 10 aniline. So this is going to be more acidic because if it gives up a proton, it ends up becoming an aromatic compound, and that's why. Okay, and then the very last question, how can proton NMR be used as evidence that a compound contains an aromatic ring? Well, if you have an aromatic ring, there's hydrogens all around. Normally, if there's hydrogens in a molecule, they'll be split by one another. They'll have, like, the neighbor will have an impact on them. But these are all in identical conditions. So because they're in identical conditions, actually these all just show up as like one peak in the aromatic region. But it is slightly de-shielded, meaning that the electron density isn't like as focused on those hydrogens. So both of those things together kind of tell us where the aromatic ring would show up, tells us that it's delocalized and it is aromatic. I am going to do another video on proton NMR. I received a request for that, so you can be looking out for that later today. All right, well, I hope this helps, and if you have any questions, please reach out. Happy studying!